Good evening, ladies and gentlemen, and welcome to our presentation. My name is Mohammed Sharare. I'm the technical engineer at Solis Depot. Solis Depot is Huawei value-added partner and also the certified service partner. Today we'll be talking about improving the efficiency of switch reluctance motors of electric cars using the Sigmoid torque sharing function. This is a proposed idea in the field of torque ripple mitigations related to applications in the automotive industry and electric vehicles when using the switch reluctance motor. Sitting by next to me is my colleague Abdullah Al-Barghouthi, and he will be introducing himself now.
Greetings everyone, my name is Abdullah Al-Barghouthi, currently working at Ghiras, located locally in Amman, and with some experience in low current systems.
We'll be talking about the motor's configuration, and then we'll be talking about its structure in general basis, and then we'll be talking about the motor's drive controller and how the power electronics are implemented in its operation, and then we'll be talking about one of the proposed ideas from researchers in the field of torque ripple mitigations related to switch reluctance motor, which is the torque sharing function, and then we'll be talking about our proposed idea from the torque sharing function, which we have proposed in our work, and finally we'll be talking about the simulation and results regarding our work.
Starting with the motor structure, as we can see on the left, a schematic of the SRM, which consists of 8 stator poles and 6 rotor poles. And starting with why it's a low-cost and robust construction motor, as we can see, there is an absence of the use of permanent magnets, and we are only using salient structured stator and rotor poles with windings surrounding the stator poles. It's suitable for high speed and high temperature conditions, as the rotor is freewheeling at the operation.
As you can see in the graph on the left of the screen, we have a graph showing the flux linkage versus the rotor position of the switch reluctance motor. Now the main principle behind the working of the switch reluctance motor is as this. Here the stator poles, which are composed from a ferromagnetic material, and here are wrapped around with windings that to be supplied with DC voltage. Supplying the DC voltage will allow a magnetization in the stator pole, which will allow the creation of the changing in the permeability of the stator pole, and then creating a traction between the rotor pole and the stator pole. This will be presenting in a variance flux linkage due to the change in the permeability of the stator poles, which are composed from ferromagnetic materials, and this change will be reflected as a variance in the inductance. This is a natural behavior of the switch reluctance motor, and this will be creating torques, and increasing the torque, it depends on the increasing of the flux linkage, and decreasing the torque also depends on the decreasing of the flux linkage, hence will be decreasing with the supply DC voltage on the windings that are wrapped around the stator pole. Now we're talking about the main component of the motor's driver, which is the asymmetric bridge converter. The asymmetric bridge converter is the unit behind the conversion from the electrical energy into the mechanical energy. As you probably can see here we have 2 switches and 2 diodes connected to each phase. The inductor symbol in the figure here is represented by the phase of the switch reluctance motor. So if we have 3-phase switch reluctance motor, then we'll be having 2 switches and 2 diodes connected to each phase. Now, the conversion from the electrical energy into mechanical energy is to be explained in 3 modes, which are mode 1, mode 2, and mode 3. In mode 1, in order to magnetize the stator pole, we'll be supplying a DC energy from the DC source into the windings. This has to happen by closing both switches S1 and S2 in order to allow the creation of current movement into the windings. Now, the diodes here are to prevent the movement of the current in the other direction, and hence to only magnetize the stator pole. So here we supply the phase with positive DC source. Now, in order to reverse the direction of the current and hence demagnetize the stator pole, we have to change the direction of the current. This has to happen by opening both the switches S1 and S2. When opening both switches, it will be creating a reverse direction of the current, allowing to demagnetize the stator pole. This has to happen by reversing the supply DC voltage from positive negative here and then reversing it into negative DC voltage, and this will allow a reverse direction of the movement of the current, hence demagnetizing the phase. We can also demagnetize the stator pole by what we like to call a natural decay. This has to happen by opening one of the switching and closing the other switch. This will allow the path of the current to move within the negligible resistance of the wires. This will create a circulated current within the phase itself and decaying at the end. Now, the difference between mode 2 and mode 3 is that mode 2 is usually used when we want to do hard switching, so that we want a fast decay for the current in order to demagnetize the phase. And mode 3 is used when we use the soft switching. Switching will take more time for the current to decay and hence to demagnetize the stator poles. Torque generation is usually used when we magnetize the stator pole, as we probably can see on mode number 1, and demagnetizing the phase can happen by either going to mode 2 or mode 3, depending on the switching schematic, which is either hard switching or soft switching.
Heading on the torque sharing function in general. As my colleague has explained earlier, feeding the stator poles one by one will create an air gap region where the rotor is not touching any of the stator poles. Therefore, we have to manipulate this region where we call it commutation region, where we let the outgoing phase decays on a longer region and the incoming phase to work earlier, where to compensate its losses to have a constant torque generation throughout the electrical cycle. As we can see on the second figure below, it represents the mathematical model of the operation of switch reluctance motor, and we are more focused on the rise and fall functions. Researchers started using the analytical TSFs in order to mimic the natural behavior of the motor, and they've used linear, cubic, exponential, and sinusoidal TSFs, where they came with many constraints. Therefore, we propose our TSF.
Next, we'll be talking about the torque sharing function, which was proposed by our work earlier this year, where we have proposed a new rising and falling functions in the mathematical model of the torque sharing function, taking into consideration the non-linearity of the switch reluctance motor, and also taking into consideration the behavior of the switch reluctance motor, allowing a better outcome in the torque ripple mitigations and hence improving the efficiency of the motor. Now, the main idea behind the proposed torque sharing function is that we have represented a new monatomic mathematical function. Now, as my colleague Abdullah has explained earlier, the already existing torque sharing functions were consisting of linear, cubic, exponential, and sinusoidal functions. Now, all these functions work just fine. However, when the motor is operating at high speeds, and also when taking into consideration the non-linearity of the switch reluctance motor, there comes drawbacks of this function, and hence we would have to present a new monatomic mathematical function in order to allow the motor to generate at high efficiency during high speeds. Now, the advanced sigmoid function has came into place. We have presented a new sigmoid function that allows the switch reluctance motor to change from its falling position going on its rising position, and hence improving the efficiency of the motor. Now, the main changes behind the proposed TSF is to change both the rising and falling functions of the mathematical model in the torque sharing function. The rising functions and falling functions were derived from the sigmoid function, while changing some of its properties in order to be used in the switch reluctance motor. The main reason behind using the sigmoid function is that the sigmoid function is an S-shaped function, which means that when compared with another analytical functions such as the linear, cubic, or the exponential functions, it has a highly slope in its S shape, allowing a faster change from the falling position into the rising position of the rotors, and thus reducing the commutation region, and then reducing by then we would be reducing the output torque ripples generated by the commutation region. Now, the main idea behind the rising and falling function is to be using the sigmoid function, which is usually used in the activation functions in applications for neural networks and artificial intelligence. Now here are the effects of changing the firing angles of the rising and falling functions of the proposed torque sharing function. As you probably can see here, this is the rising function when the firing angles are too low, and hence when we are changing the firing angles, we will be having a much higher slope. Hence the transition from the falling function into the rising function will be occurring at higher speeds, and hence the torque ripples will be mitigated in this case.
Finally, heading on the simulation and results of our work, heading on the torque and flux linkage characteristics, these graphs were obtained by the simulation tools provided by ANSYS. Flux linkage profiles and torque profiles were turned into tabulated data and to be further used in the implementation of torque sharing functions used to control the motor. Heading on the non-optimized torque generation, as we can see, the phase currents are as seen, and the commutation region is also seen in the figure A. Going to the total torque generated, as we can see that the torque generated is so distorted, and the torque ripples are getting up to 200% of the total torque generated. Heading on the optimized torque generation, we can see that the phase currents have some spikes. These came from the use. These came. Following that, the optimized torque generation, seeing the figure on the left of the phase currents, the spikes in the currents, it comes from the use of the rising function, where the incoming phase were turned on earlier to compensate the losses of the outgoing phase, but that does not matter, as the total torque generated, as we can see, is better, and we've achieved much lower torque ripples.
Next, we will talk about the implementation of switch reluctance motor in the future. Now, the global electric motor market is estimated to reach a value of $164 billion in 2022. Therefore, the research will be more focused on providing a new technologies in the field of electric vehicles and automotive industry. As you can probably see here, in 2022, the Asian region is expected to have a 63.9% of the global demand and 69.21% of the global shipment. Therefore, companies are racing with time to providing new technologies and innovations in the field of electric motors. And also, not to forget that several tech companies are investing in switch reluctance motor technologies, and research facilities are coping with the growing demands of affordable electrical vehicles, because the existed electric vehicles which are be using with conventional electric machines and electric motors such as induction motor will be facing the problem that it requires more material and it requires more rare earth materials, and therefore we have to find a solution that compensate the use of environmental resources so that we can provide this growing demand in the electric vehicles. Because the environmental impact plays a huge role in the focus of the research in the switch reluctance motor due to the absence of the permanent magnets, which are considered in today's electric motors as the main important system. So therefore, they are considered as rare earth materials. Therefore, we have to focus more on the environmental impact. And also not to forget that the maintenance plays a key role in the operation of SRMs, as they are requiring less sustainations due to their robust construction and easy to maintain. Therefore, it would be more easy to implement in the future designs and the future applications of the automotive industry. Here we have reached the end of our presentation. We would like to thank you so much for your attention, and we hope to see you soon in future presentations. Thank you so much.
Thank you so much.